Assalamualaikum and greetings to all. Today's topic is on implicit function. Before we proceed with implicit function with two independent variables, let's refresh our memory on implicit function with one independent variable. Okay, let's proceed to, let's go straight to an example. So here we have, we need to find dy dx if y is defined implicitly as this. Okay, so to do this, we need to differentiate both sides with respect to x. Okay, so for this example, the equation is y to the power 4 plus 3y minus 4x cubed, and on the right hand side we have 5x plus 1. So what we need to do is we need to differentiate both sides with respect to x. Okay, so differentiate a term at a time to both sides, left hand side and also right hand side. Okay, keep in mind you have to differentiate when you see x and also when you see y. Okay, the first term we have y to the power 4. Differentiate that, we get 4y cubed times dy dx using the chain rule because y is differentiable with respect to x. And the second term we have 3, differentiate y, we get dy dx. And the third term we have 12x squared. And we do the same thing on the right hand side. Differentiate 5x, we get 5. Differentiate 1, we get 0. And the next step is to factor all the terms with dy dx. So we have 4y cubed plus 3. And the terms without dy dx, we have 5 plus 12x squared. And the last step is to divide both sides with the expression inside the bracket here. So we have 5 plus 12x squared over 4y cubed plus 3. Okay, this is obtained from implicit differentiation. This is called implicit differentiation. Okay, now apart from using implicit differentiation, you can get dy dx by using the formula. So here we have a formula. The theorem 2.4, it says if fxy equals 0 defines an implicit function with fx, then dy dx is equal to negative partial f partial x over partial f partial y. So this formula is obtained from using the chain rule. I'm not sure if you're interested in how to get the formula, but let's see here. So first step is you have to rewrite your equation as fxy on one side and 0 on the other side. So that's the first step. Okay, and then we're going to introduce a variable. Let's say we let u equals x, this one, okay, and y is a differentiable function. And then we're going to introduce w as well. So let's say w is equal to f of xy. And since we let u equals x, so we can write w as a function of u and y. And then we can draw a tree diagram. Okay, so from here we have w is a function of u and y, so branch out to two branches. U is equal to x, y is a function where it is differentiable with respect to x. Okay, and then we want to find dw dx. We're using d here because we only have one independent variable. Okay, so since on the far right we have two terms, we have two x's, meaning that we have two terms. So here we have dw dx is equal to partial w partial u from here to there, and then du dx, since u is equal to x, so it's going to be ordinary derivative du dx. And the second term we have partial w partial y times dy dx. And since w is equal to 0, dw dx, differentiate that, so it's equal to 0 because when you differentiate 0 we get 0. Okay, so this is equal to 0. Okay, but we know du dx is 1. Okay, so this part here is equal to 1. So from there we get dw dx is equal to partial w partial u times 1 plus partial w partial y times dy dx, and this is equal to 0. And then doing some mathematical manipulation, we get dy dx, we can write here, is equal to negative partial w partial u, and then dy dx is equal to negative partial w partial u over partial w partial y. Okay, but then remember before w w is equal to f of xy, or when you let u equals x, w is equal to f of uy. So we can also use f instead of w, since w is equal to y, so we can write this down as negative partial f partial u. But remember, u is x, so we can write this down as partial f partial x, and here we have partial f partial y. So that negative there is obtained from mathematical manipulation. So from here we get the formula from theorem 2.4. First of all, we have to rewrite the equation as f of xy equals 0. Then from there we get dy dx is equal to this. Okay, now I'm going to use the same equation, the same example, but I'm going to use the formula instead to find dy dx. In the first example, I've shown you using implicit differentiation. So now I'm going to use the same equation, but we're going to use the formula. Okay, all right, so first step, we have to rewrite this equation as f of xyz. So sorry, f of xy, no z yet. Okay, so I'm going to rewrite this as y to the power 4 plus 3y minus 4x cubed minus 5x minus 1 equals 0. Okay, that's very important. You have to rewrite the equation as f of xy equals 0, then you can use this formula. Okay, according to the formula, dy dx is equal to negative partial f partial x over partial f partial y. Okay, for partial f partial x, we differentiate this with respect to x by holding y as a constant. So that will give us 0. The first term will give us a 0, second term also 0, the third give us negative 12x squared, and the next term is negative 5. Oops. And in the denominator we have partial f partial y, so now we differentiate with respect to y, so we get 4y cubed plus 3. So simplify this, we get 12x squared plus 5 over 4y cubed plus 3. Okay, we got the same answer as using implicit differentiation. Okay, now we can extend this to function with two independent variables. So I'm not going to go over how to get the formula. I'm just going to show you the formula. The step or the procedures are the same as before. Okay, so now I'll go straight to example, the next example. Before we go to the example, let's look at the theorem. If f of xyz equals 0, so it's very important to rewrite your equation as this, implicitly defines a differentiable function z as a function of two variables x and y, then partial z partial x is equal to this equation. Again, you can see that we have a negative there, and partial z partial y is equal to that. Okay, I'm going to go straight to example. Okay, so here we have our equation xy squared plus zy equals negative x sine z. As you can see, it is very hard, or it's quite impossible to write z in terms of x and y here. So here z is defined implicitly. Okay, first step, we need to rewrite the equation so that we have all the expression with x, y, and z on one side. So that will give us xy squared plus zy plus x sine z equals 0. Okay, to get partial z, partial x, we need to find partial f, partial x. So differentiate f with respect to x by holding y and z as constant. So the first term will give us y squared. Next term will give us a 0. Next will give us sine z. And we also need partial f, partial x, z. First term will give us a 0. Next term will give us a y, because we differentiate with respect to z here. And the last term will give us x cos z. Okay, so from using the formula, partial z, partial x is negative partial f, partial x over partial f, partial z. So that will give us negative y squared minus sine z over y plus x cos z. Okay, and for partial z, partial y, we need fy. Okay, differentiate f with respect to y will give us 2xy for the first term. The second term will give us a z. The third will give us a 0. Okay, so partial z, partial y is equal to negative partial f, partial y over partial f, partial z. Okay, so we get 2xy plus z over partial f, partial z, which is y plus x cos z. Okay, so this is using the formula to find partial z, partial y, and partial z, partial x for implicit function. We use the formula, or you can also use implicit differentiation, like the method that I've shown you, the first method, using implicit differentiation, where you differentiate both sides with respect to x or with respect to y. Okay, that's all for today. Thank you.